welcome to the deep dive. You gave us a fantastic stack of sources, a major strategic report, and some really deep engineering analyses. And today our mission is to synthesize the two biggest revolutions hitting the automotive world right now.
And they are truly massive.
On one hand, you've got the unstoppable rise of the software-defined vehicle, the SDV.
Right.
The car is basically becoming a computing platform. And on the other, you have this fundamental technical shift in the hardware to the incredibly demanding 800-volt platform.
Even beyond that.
Exactly. We've gone through a huge industry report from ProStep, IVIP, and EY on how to navigate this SDV transition.
And we've also mastered the electrical physics behind the move from the old 400-volt systems to 800V and even 900V.
So our goal today is to connect that high-level software strategy with the high-stakes engineering reality. Okay, let's unpack this. And I think we need to start by understanding just how big this change really is.
It's almost impossible to overstate. I mean, the data we pulled from that industry analysis is just staggering. By 2030, it's projected that 9 out of every 10 cars sold will be software-defined vehicles.
9 out of 10.
Think about that. We went from just 1 in 10 in 2023 to basically 90% in just 7 years. This is not an evolution. It's a complete reimagining of the car.
So it's moving control
From fixed hardware, what you buy on day one, to flexible software that can be updated, that can evolve over the life of the car.
that sets the scene perfectly. So we have these two huge simultaneous projects happening.
Right, happening at the same time.
The business challenges of the whole SDV ecosystem, and then the really intense engineering trade-offs you have to make for high-voltage hardware. So let's start with the why. What's the commercial driver behind this whole software transformation?
Well, at its core, the SDV is just a vehicle where its features are mostly added and improved through software updates.
Throughout its entire life.
Exactly. It's the complete opposite of the traditional model, where the car is basically finished the moment it leaves the factory.
And the reason every big automaker is betting their future on this is laid out so clearly in what the report calls the SDV value pyramid. The financial promise is just huge.
It is. New revenue streams from features on demand, subscription services.
And the research estimates these could generate up to, what, $500 per vehicle every year.
That's the number they're projecting.
But tell us, what are people actually paying $500 a year for? It sounds a little vague.
Well, it's actually highly specific. And it's recurring revenue, which is the key. We're talking about things like enhanced driver assist packages you activate after you buy the car.
Okay.
Or maybe remote start functionality, even temporary performance boosts. Or say you live somewhere cold. You might subscribe to heated seats for just the 3 winter months.
So it's reliable money.
It's reliable, predictable money, and that's what investors find so valuable. But it goes beyond just the cash. There's a huge operational advantage here.
Yeah.
By using what the software world calls CI/CD continuous delivery pipelines, the cars stay competitive long after they're sold. A 4-year-old car can get a major update to its safety or efficiency systems.
So you're extending its product half-life.
You're extending its half-life, exactly. It stays relevant.
That makes sense, but if software is really eating the car, that must just completely upend the old automotive hierarchy, right? Who loses out here? Are the traditional Tier 1 hardware suppliers just irrelevant now?
That's where the complexity just explodes.
Yeah.
The ecosystem now has cloud giants like Microsoft and IBM in it.
And chip manufacturers.
Huge chip manufacturers, legions of software engineers, all trying to work with the traditional parts makers. So those Tier 1s are scrambling. If their component can't be updated or integrated through software, their value just plummets. The old boundaries are just dissolving, and it's creating a ton of friction.
And this is where the experts in that ProStep IF report really lay out the reality of it. They flagged 6 critical categories that are holding back real progress on the SDV.
Right, it's not just one thing. It's a whole set of systemic hurdles.
So let's dive into them.
Okay, let's start with 2 that are really about mismatched expectations. First is regulatory misalignment.
Right.
Automakers are global, but the regulations are all fragmented and regional. You're trying to comply with UNR 156 in one place.
And then AIS 190 somewhere else.
Exactly. So your global software rollout gets slowed down, or you have to disable features in certain markets. It's a mess.
And the second one, you hinted at this, the collaboration gaps. This is the real culture clash.
It is. You've got the slow, linear, safety-first V model of traditional auto engineering.
Which is all about ISO 26262, ACE by CIS, very rigid standards.
And that is clashing directly with the rapid, continuous DevOps model from the software world.
I heard this great anecdote about that. You have one side saying, we need 18 months for physical validated proof of failure.
And the software team is saying,
We push updates every night. Which version are you even testing? They're on totally different clocks.
that is the tension. Exactly. It's a clash of speed and a clash of risk tolerance. And this feeds right into the third challenge, lack of standardization. Oh, absolutely. We're still seeing incompatible data formats, proprietary APIs, inconsistent protocols between different ECUs.
So every platform is a custom job.
It's all expensive custom workarounds instead of scalable solutions.
The fourth one is more operational, right? The complexity in processes.
Yes. Companies are really struggling to integrate their application lifecycle management, how they build the software, with their product lifecycle management, which is how they manage the physical car.
So you can't track which software is on which piece of hardware.
And if you can't do that efficiently, compliance just becomes an absolute nightmare.
And the fifth one sounds like the most frustrating of all, digital homologation.
Oh, it's a huge bottleneck. This is getting regulatory approval for any safety-critical software update.
And the report said it can take up to 4 months.
Up to 4 months. And it's not just bureaucracy. It's because regulators need a verifiable, physical paper trail to assign legal responsibility for safety. The whole manual process just kills innovation speed.
We have to move from that paper trail to a digital one,
Yeah.
which I guess brings us to the last big hurdle, the talent shortage.
Yes. The skills you need, AI engineering, cybersecurity, advanced computer science, they just aren't common in the traditional automotive workforce.
So OEMs are now competing with who? Silicon Valley.
They're competing directly with Silicon Valley, the gaming industry, you name it. And that means huge salaries, high turnover, and just the massive cost of trying to poach the talent you need to build all this.
Okay, so that's the SDV story. It's a race for new revenue, but it's held back by all this organizational friction. Now, let's pivot completely. If the software is all about moving fast.
The 800-volt hardware is all about managing the intense speed and heat that comes with it.
Exactly. We're now in what people are calling the Gen 3 EV. Dedicated platforms, OTA updates, and critically, this 800V architecture.
And this is all driven by just fundamental physics. You want high charging power, which is P.
Power equals voltage times current.
Right. P equals U times I, so you have to increase one or the other. And automakers are strongly preferring to increase the voltage, the U, over the current, I.
Why is that preference so strong?
It's all because of the geometrical heat penalty. Resistive heat is proportional to the square of the current, I squared R.
So if you double the current,
You quadruple the heat. To get, say, 250 kilowatts of charging power in a normal 400-volt system, you need a peak current of over 600 amps. The heat load, the cooling systems, the thickness of the cables, it all becomes massive.
and with an 800-volt system,
Well, a car like the Porsche Taycan only needs around 340 amps to get that same 250 kilowatts.
wow.
So that reduction means the 400-volt system is generating roughly 3.28 times as much heat for the same power delivery. That thermal reduction is the absolute game changer. It lets you use thinner, lighter copper cables everywhere, which saves a huge amount of weight.
That weight saving is a massive advantage. So let's see how this plays out in the actual components, starting with the battery pack.
Okay.
We can compare a 400V pack, like in the Tesla Model 3, to the 800V Taycan or even the 900V Lucid Air. The payoff is pretty obvious. The Taycan gets from 10 to 80% charge in just 19 minutes.
Compared to the Model 3's 27 minutes.
That's just pure speed. But what's the cost of that speed? You mentioned complexity. Is that speed benefit really worth doubling the complexity and the cost in the battery pack?
Well, that's the big question. To double your pack voltage from 400V to 800V, you basically have to double the number of cells you connect in series.
So you go from, what, 96 to 192 cells?
Something like that, yeah. And every single one of those cells needs to be monitored. So that makes your battery management system, your BMS, way more complex and expensive. You need more voltage sensors, more fuses, beefier contactors. It's a huge trade-off, but the market is demanding that faster charging.
Okay, so let's move to the inverter. This is the core power electronics that converts DC from the battery into AC for the motor. This is where high voltage really starts to stress things.
It does. To handle an 800-volt bus, you have to move away from traditional silicon IGBTs and adopt high-voltage silicon carbide MOSFETs, or SiC. You need devices rated for around 1200 volts.
And 6 is great for efficiency, but it brings its own problems.
It does. Its fast switching creates all sorts of new electrical issues, and the solution is something called a multi-level inverter, or MLI.
Okay, what is that?
The best way to think of it is like splitting a big electrical hill into 3 smaller, manageable steps. Instead of forcing one semiconductor to handle the full 800 volts, And MLI splits that voltage across multiple devices.
And why do that?
Two big reasons. One, it reduces the electrical stress on each component so they last longer. And two, crucially, it massively lowers the electromagnetic interference, or EMI noise.
Which we care about
Because high EMI noise can cause something called bearing currents. It's basically stray electricity that jumps across and degrades the motor's metal bearings, causing the motor to fail prematurely. So MLIs help keep the motor healthy under these extreme conditions.
Let's talk about the motor itself then. The higher voltage allows for higher speeds and much better power density. And this metric, power density, that's the holy grail, right?
It absolutely is.
And the contrast is just amazing. The Porsche Taycan motor is around 7.4 kilowatts per kilogram, but the Lucid Air motor is almost double that at 14.5. Why is that specific number so important for you as a consumer?
It all comes down to physics and packaging. Power density is how much horsepower you get for every pound of weight. Getting 14.5 kilowatts per kilogram means you can deliver huge performance, insane torque and speed with a motor that is physically much smaller and lighter.
And that saves space and weight can go back into.
More passenger room or more battery for more range. It's a virtuous cycle.
But there's always a catch.
With high voltage, there's always a catch.
Yeah.
Here, it's the risk of partial discharge, or PD. Those super fast CDIC inverters can cause these sudden voltage spikes at the motor terminals that can reach up to 2 times the DC link voltage.
So on an 800-volt system, you're seeing 1600-volt spikes.
You're seeing 1600-volt spikes hitting your motor windings, and those spikes can break down the wire's insulation, that's the partial discharge, and lead to a catastrophic failure.
So how do you possibly fight back against a 1600-volt attack?
With a lot of advanced mitigation. You use thicker insulation on the wires. You do this incredibly thorough process called vacuum pressure impregnation on the windings to get rid of any air gaps.
And you use those multi-level inverters again.
And you use the MLIs again to smooth out those voltage steps. It's a constant battle between speed, power, and long-term durability.
Okay, let's wrap up the hardware with the onboard charger, the OBC. It also has to be upgraded to 1200-volt components, but the real innovation here seems to be about integration.
Absolutely. Manufacturers are getting really clever. They're repurposing the high-power electronics they already have.
Like using the main traction inverter.
The thing that drives the wheels to temporarily function as a charger. It reduces redundant hardware. A great example is the Wonderbox in the Lucid Air. It can act as a step-up converter.
So it can charge its 900-volt pack from an older 400-volt fast charger.
Exactly. It bridges that compatibility gap right on the vehicle.
Okay, so if we connect this all back together, we've got these two immense transitions, SDV and 800V, both driving complexity, cost, and risk. The industry can't solve this alone in silos.
They can't.
Yeah.
You need these collaborative initiatives to standardize how this super complex hardware integrates with the super complex software ecosystem. You have to bridge that organizational chasm we talked about earlier.
Which brings us full circle to the 4 big initiatives that organizations like ProStep IVIP are pushing for, designed to systematically knock down those 6 roadblocks.
That's right.
First, a big focus on software component traceability, using something called a software bill of materials, or SBOM.
This is all about accountability. In that huge web of vendors and cloud providers, you have to know exactly which line of code is running where.
Second is the need to advance digital homologation.
We just can't keep waiting 4 months for a manual safety approval. The goal is to automate that with a verifiable digital twin that regulators can trust as much as a physical test bench.
So you can deploy features at software speed.
At software speed. Third, and this might be the most critical for the culture change, is fostering effective collaboration.
Getting everyone to speak the same language.
Exactly. Creating specific forums and guidelines to bridge that gap between the slow-moving OEMs and the fast-moving software providers.
And finally, a long-term investment. Develop integrated university programs.
You have to build the talent pipeline right now. Direct partnerships with academia to teach students the specific skills they need. A blend of software engineering, AI, and deep automotive knowledge.
So to recount the core learning for you, this shift to the software-defined vehicle and the 800V architecture isn't really optional. It's a non-negotiable transformation being driven by what you demand as a consumer and by just fierce market competition. We've seen that high voltage gives you these incredible benefits, faster charging, more power, less heat, but it places these incredibly stringent demands on everything from insulation and component cost to industry-wide standards.
And the key takeaway is that this transition isn't about choosing to be good at software or good at hardware. It's about mastering the brutal complexity of integrating them seamlessly and reliably across every single layer, from the materials in the battery all the way up to the simulation and the digital twin. That is the real challenge.
So what does this all mean for you as someone following this industry? Well, while 800 volts is solving today's problem of fast charging, how long is it until the inevitable jump to post 1000-volt systems? A jump that will demand the next generation of materials, completely new inverter designs, and radically different regulatory frameworks. The need for this continuous system-wide transformation, it's permanent.
That's a great way to put it.
Thank you so much for joining us for this deep dive into the future of automotive technology. If you found this useful and you want more of this kind of analysis in your feed, be sure to follow us to stay informed and get the full breakdown next time.